Now, I'm going to pause here for just 1 second, because I know some of you guys are going to come back and you're going to start listening to this lecture, and you notice every now and then I'll kind of look down to see if the lights are turned on and stuff. That just tells me the battery's working. Just looked down and the battery was off on this, so I just turned it on. This will happen on many occasions. There's a lot of user error, especially at 4 o'clock in the afternoon. So the first 45 minutes you can kind of just say, all right, go and listen to the old lecture. All right, if you're interested in listening to it. All right, protein-mediated transport. All right, now what we're describing here is basically saying, look, all the proteins in the body are not lipophilic. If they were, then we'd have a real problem. Most of the proteins in our bodies, or most of the molecules in our bodies, are lipophobic. All right, they're water-loving, they're charged molecules, and so they're prevented from passing through the membrane, and so we need some way to get them around. And so this is where we're going to use that facilitated transport. Facilitated means help, all right? And this is done usually through a protein, all right? And then we have active transport. Now, well, I should stop. Facilitated transport is a passive activity, and it will allow for molecules to keep passing through the membrane until you reach equilibrium on either side of the membrane of whatever it is that you're trying to move. So remember that chart I showed you where I had a whole bunch of sodium on the outside of the cell and very little sodium on the inside of the cell? So if we had a channel, some way for that sodium to move, sodium would continue moving inside the cell until those two levels became equal. All right? Active transport, on the other hand, requires energy. And what we're trying to do with active transport is we're trying to move things against the gradient in which they would naturally travel. So what we're doing is we're saying, okay, here I have a whole bunch of sodium, here I have a whole little bit of sodium. With active transport, we're still trying to move sodium in this direction. It's kind of like lifting a box onto a shelf. Box doesn't want to go on the shelf, box wants to be on the floor. So what you're doing is you're putting it in a direction it does not necessarily want to go. Now, we pause and we come back to our membrane proteins. Because I want you to understand, when we deal with membrane proteins, we can classify them by how they're associated with the membrane, but we also classify them for what they do. Now, we're going to be focusing on the transporters, but I want you to understand that that's not the only type of molecule that's found in the membrane. We have those structural proteins that allow us to maintain the shape. What we're talking about are cytoskeletal elements, things that create cell junctions, things that stabilize tissues. And what it does, it allows the cells to actually attach to what we refer to as the extracellular matrix. That glycocalyx plus any of the proteins that are found outside the cell. So that's what we refer to as a structural protein. There's not a picture up there. We have enzymes, and the purpose of enzymes are to catalyze chemical reactions at the cell membrane. All right? Some of these molecules are going to allow us to transfer some sort of signal from the external side of the cell to the internal side of the cell, and do so by catalyzing a chemical reaction. Not all of them do that, but most enzymes associated with the plasma membrane are trying to create a chemical reaction that occurs there because some sort of activity needs to be at that level. It's not going to just be anywhere randomly inside the cell. What we'll spend a lot of time talking about over the course of the semester are receptors. And the purpose of a receptor is to receive a chemical message and then respond to it by creating some sort of change inside the cell. Now, the first thing we're going to talk about with regard to the receptors is how they play a role in vesicular transport. But you get the idea. Receptor, by its name, says I receive a message and I'm going to respond to it. And what we want to focus on are the transporters right now. All right? And so these move molecules across our membranes. And there are two different ways that we can do this. We can create a channel or a door that's always open, or we can carry something. All right? So, a channel protein is exactly what it says. It creates a pore, a channel, a tunnel through that lipid bilayer. All right? And so this is an example of a channel. You can move in either direction depending upon the gradient, and you're just passing through. It's like us opening this door over here and leaving it open. It's now a channel. People can come in and go out as they please. You can do that anyway, but you get the point. The carrier molecule, on the other hand, has a specific binding site. and it's open to a specific side of the membrane. And so when one of those chemicals that can bind to that binding site binds to it, it causes a change in that carrier molecule, in the shape of it. And what will happen is that it will close up and then open up on the other side. Now my hand can't do it quite the way that this does, but that's what we're trying to show here. All right? The carrier is open one way, and then when it gets bound up, it closes. It never creates a complete channel. It closes and opens up the other way, thus allowing that molecule to move from one side to the next. So that's a carrier. And you can think of it, I'm taking something and I'm carrying it across the membrane and dropping and letting it go. The easy way to think about it. Big ugly chart. Do you have to memorize it? No. It's there to help you. So if you're sitting there going, oh man, keeps talking about all these different things and what they're doing, you have something like this that allows you to kind of see the relationship between all these different things. And so here you can see over here are transporters. There's two different types. Over here, structural proteins. We didn't really talk about what they are, but this is what they do. Membrane enzymes, so on and so forth. I mean, it's real easy to just look at something like this and go, oh, well, now I see how they're all related because we're talking about membrane proteins. All right. So we're focusing on the channel proteins. And so you can kind of see in our little cartoon here how it creates this channel. There's all sorts of transmembrane components to it that go in and out. And what happens is you create this little tiny channel that's actually very small and very specific to what it allows it to move through. Now, if it allows the passage of water, we refer to it as an aquaporin. And there are many different types of aquaporins that are very specific for cell type and stuff. But you can see here, when you hear aquaporin, that's a water pore, and it allows for the passage of water back and forth across the membrane. Water is a polar molecule, and so this is one way it passes through the membrane. You want to know the other way? It violates all the rules that you're going to be learning. It just kind of works its way through. All right, even though it's a polar molecule, it is small enough that it actually just kind of sneaks through. Great, thanks. I just blew everything. All right, but it's the only molecule that does that. The other type of channel that we are going to see, and we're going to see a lot of them, are the ion channels. And when we talk about the ion channels, we're going to be very specific. We're going to just say, oh, this, or I should say very non-specific. We're going to say, oh, this is a sodium voltage-gated ion channel, or this is a potassium mechanically gated ion channel, or this is a leak channel that allows for the passage of whatever, calcium. All right? Here's the thing. There are hundreds of these types of channels. And when I say hundreds, I'm not exaggerating. So when you hear the word leak channel, that's a generic term. And there have been hundreds of named leak channels for a specific type of ion. Good news. We don't have to learn them. I just want to point it out because you're going to learn these things as you go along, and you'll find out that they have specific roles. Like the ion channels that are found in the brain are different than the ion channels that are found in the heart. Yay. All right. The other thing is that they're very selective. You notice I gave them a name. Like I said, this is a sodium voltage-gated channel. All right. So when you see the term sodium, you know the only thing that will allow it to pass through is sodium. Now take a look up here on the periodic table. I'm glad this room actually has one. Usually I have one that doesn't teach it. All right. We have sodium channels and we have potassium channels. Sodium is a smaller or larger molecule or ion than potassium. Smaller. All right. So let's say we have a potassium channel. Do you think sodium can get through it? You would think so because you think smaller. But the answer is no. I mean, both of those ions are the same charge. One is smaller than the other, so you'd expect the potassium channel to allow sodium ion to pass through, and it doesn't. And it's because of the way that these molecules are made. Everything inside here are charges. And so it's like, I can't remember what the name of those machines are. Some people call them plink, Chinese pinball. You know what I'm talking about? What's, huh? Plinko, all right. But basically you end up with this little metal ball that bounces around over and over again. That's what it's kind of like. These ions go through and they only fit just like those balls can fit through those little tiny slots. All right? Just because you're smaller doesn't mean that you can get through because the charges are going to prevent you from doing it. And so you can't even get through if you're even a smaller molecule. So these are highly, highly selective channels, yes. I would say yes, but Okay, because carrier molecules or carrier proteins recognize specific shapes, right? And so if you have a family of molecules that are very similar, so for example, glucose and fructose are very closely related, if they have the same, if you get the same bindings or the binding site that can recognize the same configuration between those two sugars, then that carrier molecule is going to carry both, or you'll see competitiveness between that. But you can also have a carrier molecule that's very specific and will only recognize glucose. All right. So, answer is yes, but as is always everything in biology. Yeah. That's correct. Facilitated diffusion. And the reason it's facilitated diffusion is because all we're dealing with here are concentrations, right? If I have a lot of this ion on this side and very little of ion on that side, it doesn't matter which side it is. If I have a channel in there, where are we going to go? We're going to go down our concentration gradient. If it's this way, which way are we going to go? We're going to go this way. All right. Now, channels exist in two different forms. They exist in an open form or a closed form. All right. Generally speaking, all channels, regardless of whether we call them gated or not, have some sort of gate, meaning they have some sort of door. Right now, our doors here are closed, but if we took our doors and we opened them and kept them open like that, we would still call this a doorway because it has doors, right? Even if we took these doors and we nailed them to the walls, there's still doors there. They're just non-functional doors. And so open channels spend most of their time with their gates in the open configuration. And so when we look or talk about open channels, we refer to them as leak channels because they allow whatever their particular ion is to leak in or out of the cell. All right? If it happens to be a water channel, we call them water pores because it allows water to move in and out of the cell. Yes, sir.
So the two-cell door is different. The one can be open while the other is closed. I think it just happens.
Right. All right. So that's something more specific. And so there are some channel molecules that have more than one gate. All right. And so if you have more than one gate, basically one gate has to be open and allows movement. The other one's going to be closed, which won't allow movement. Is that what you're meaning?
Right.
Yes. So that can occur, which falls into that whole category. There's hundreds of types of channels, and we're going to be very generic for right now. All right. Whereas when we're talking about gates or gated channels, we're talking about a state where those gates can be in a closed configuration or an open configuration, and something needs to occur to put them in the open configuration. Now, I've put 3 examples up here. Voltage-gated channels are going to respond to changes in ion concentrations. In other words, changes in the electrical state of the cell. All right. Chemically gated channels are the easy ones to think about because it's like a lock and key. You expect some sort of molecule to come along, bind to the channel, causes the gate to open. And it's like a lock, stick it in the key, open the door. All right. But we also have mechanically gated channels. We have thermally gated channels. We have osmotically gated channels. I mean, there's all sorts of fun stuff. All right. And so you can see that there are specific stimuli that can open and close the gate. And that's how we define these closed channels. We just call them blank gated channels. Now, when these gates are open, our movement is going to be down their concentration gradient. It's facilitated diffusion. It allows you to move down your concentration gradient. The carrier protein, on the other hand, is more specific in terms of what it's binding. I shouldn't say more specific, but you can see what we're doing is we're moving a molecule. We're binding to a binding site. We're open up to a specific side. Once we get bound, we open up to the other side, and that allows for that molecule to move through. It's a change in the configuration. All right? We never create a continuous passage, and we're moving things from one place to the other. And because we don't open a gate, because we're moving things where we have to go through several steps, it's a lot slower. Now, let's think about movement through a door. If I open the door and say, everyone rush out, you guys would start moving through. But what if this door was not one of these, but one of those rotating doors? It would take longer. Yeah. And that's like what this is. It's like a rotating door. You have to go in, get in your compartment, and wait till it opens up to the other side. A lot slower. Now, we classify carriers based upon how many molecules they actually carry. All right, they can be a uniport carrier, which means they carry one molecule, or they can be a co-transporter, where they carry two or more. And we're going to be talking about where they actually carry two, but there are plenty of co-transporters out there that carry 3 molecules, and even some cases where they carry 4. But that gets confusing and it's horrible to think about, so we'll keep it simple. All right? And so uniport, we're always going to carry one kind of molecule. With co-transporter, we're going to be carrying 2, and then we have to consider how are we carrying these molecules. Are we carrying them in the same direction, or are we moving things in opposite directions? And when we move things in the same direction, that's called symport, and we're moving in opposite directions, it's antiport. All right? And that's what these two things, it's interesting, are doing over here. Here's our antiport. We're moving sodium in one direction, potassium in another. Here, we're moving sodium and glucose together. So with facilitated diffusion, as a general thing, whether it be a channel or a carrier, we're moving downhill where we're not using energy. And so you can use this as an example. Here we have high glucose on the outside of the cell. Glucose outside the cell is useless, right? So we want it inside the cell, so we can use a transporter. In this case, it would be a carrier molecule that allows us to move glucose from an area of high concentration to an area of low concentration inside the cell. But once the glucose inside and outside the cell are equal, we no longer move. All right? We've reached equilibrium, and so glucose isn't going to move out or move into the cell any more than it's going to move out of the cell. Our net diffusion has ceased. This poses a problem, especially in the case of glucose, because it took a lot of energy to get that glucose into your body. And that glucose needs to be inside cells. So what happens is if we want to continue to move something down its concentration gradient, we have to convert it. And so in this case, what we're looking at is where glucose gets changed into glucose 6-phosphate. And by doing so, what have we done? We've kept the concentration of glucose low, and that continues to allow for there to be a concentration gradient to move materials in. Now this happens all the time. I'm just using glucose as an example. If we want to move materials into the cell, we have to maintain that concentration gradient. So once something moves in, what we've done is we're starting to decrease that gradient, so we have to do something on that downside to make sure that we maintain the steepness of the gradient. So when equilibrium is reached, no further net diffusion, so we have to compensate for that or make adjustments. Now active transport, on the other hand, is energy dependent. And there's 2 different types of active transport. We have primary active transport, which you already know about, which we're going to talk about still, but you've seen it before. And then secondary active transport, which you've probably seen, but you're basically you said, yeah, I'm not going to learn that. All right. And here, again, we're going to use a carrier to transport molecules across the membrane, but we're moving things against their gradient. We're moving things in such a way that we are pushing things away from where they want to be. All right. So with primary active transport, we are going to be directly using ATP. Generally speaking, the molecules that are involved in primary active transport are ATPases. In other words, they're enzymes that catalyze the breaking of ATP to release the energy to change the shape of their own molecules. We're going to see an example of the most classic example, which you've learned about, the sodium-potassium ATPase pump. And notice what I just call it. Call it a pump. Most of these molecules, these ATPase transporters, are called pumps because we're pumping molecules away from where they want to be. All right? Secondary active transport is a little bit more confusing. Because we're moving things against their gradient and we're creating these large concentration gradients, what we've done is, in essence, we've stored up energy. Right? If I create a huge gradient, that's going to be something that I can take advantage of as those molecules move down to that area of low concentration. And what secondary active transport does is it takes advantage of that energy. So it doesn't use ATP directly, but in order for me to create this imbalance, I have to somehow use primary active transport to create that. All right? So secondary active transport takes advantage of the energy used here in the form of potential energy. Now let's take a look first here, and then we'll come back and look at secondary active transport. So it'll make sense. Here's a sodium-potassium ATPase pump. All right? What we have is we have a molecule that's capable of binding sodium and a molecule that's capable of binding potassium. depending upon its configuration. It can bind 3 sodium molecules or 2 potassium molecules. What it's dependent upon is the presence of ATP to cause a change in its configuration. So what happens is in its open state, when it's open inside the cell, or facing inside the cell, the configuration on the inside has greater affinity for sodium than it does for potassium. So sodium moving around will find and bind to those sodium sites, and once 3 of them are bound, it makes available the ATPase site. And so ATP comes along, and what we do is we take the energy of that ATP, which causes a change in the shape of the molecule. And when you change the shape of the molecule, you lose the affinity for sodium. So when you started out like this, I like sodium. When you change shape so that you're now facing this way, you no longer like sodium. And so the sodium, not being liked, is going to bail. And so it leaves and goes on the outside of the cell into the extracellular space. But at those same exact spots where that sodium was, you've changed the shape of the molecule, so now it has an affinity for binding potassium. And so potassium, which is on the outside of the cell, will kind of wander in and bind to its site. And once those 2 potassium bind to their binding sites, and yes, I know they're drawing them on the opposite side, they're just doing that for your convenience, then that's going to cause a change in the shape of the molecule once again to close up and then reopen to the inside so that the potassium can then move out of the cell. And now we're in the same configuration we started. The difference is we've moved 3 sodium out of the cell and we moved 2 sodium in the cell. All right? Now where does sodium want to go? It wants to go inside the cell. Where does the potassium want to go? Outside the cell. So what we've done is we've created a gradient, right? We've moved, by using a little bit of energy, we've moved molecules, and now we have potential energy that we can take advantage of. And so the benefit, the plus of having these type of pumps is we can now have potential energy that the cell can then use. It's kind of like having a built-in battery. We're just taking advantage of the concentrations of ions in the different compartments that we started talking about at the beginning of class. All right? So what we have here is potential energy. Now, I'm going to move to secondary active transport so you can see one of the ways that we use this potential energy. As I said, glucose desperately wants to be in the cell. All right? Because that's where it has the most use. If you have it floating out outside the cell, it's totally useless to you. Glucose is only useful to you where it can be used for energy, to release its energy that's found inside that molecule. Problem is you don't want to use energy to move that molecule. That doesn't make any sense, right? I mean, think about all the effort it took to walk down to the UC Underground and buy your 6 burritos, right? And how much energy it took you to consume those burritos, right? And then walking back up the stairs. I mean, there's a lot of energy involved there. So you don't want to waste energy just moving the glucose from your digestive tract into the cells that are going to use the energy, right? So you need a trick, or you need a trick, to get the glucose into the cells without using energy. Problem is all of the glucose in your body to begin with is where? Inside cells, right? Because that's where it's going to be most useful. So all the glucose that you already started with before you ever went and bought the burritos is inside the cell. So you already have high concentrations of glucose inside the cells, and you have low concentration outside the cells. So when you buy the burritos and eat the burritos, you're building up the concentration of glucose. And which way is your gradient? It still favors glucose moving outside the cell. So you're going to have to use energy somehow. And here's where the trick for secondary active transport comes in. Remember what we said about sodium? Sodium, which has been pumped out of the cell, is desperate to get back inside. Please, I want to go back inside the cell. It's much more safe. And glucose says, hey, psst, I need to get inside the cell. I've got this transporter over here. If you come with me, we can get inside the cell together. And that's how it works. Sodium binds to its binding site inside this co-transporter. And that's what it is. Secondary active transport is a sodium glucose co-transporter. So it binds to and makes available the binding site. So you see, sodium can't get in on its own. Glucose doesn't even have the affinity until sodium binds. And then what you do is you make that binding site available. So now glucose can bind. And when glucose binds, That's when it changes shape and opens up. And so glucose and sodium can pop out. This is a lot like ladies' night. All right? Ladies can go into bars for free. Guys are stuck on the outside going, but I want to go in where the ladies are. And that's exactly what's happening here. All right? We use the energy of the concentration gradient of sodium to drive the movement of glucose into the cell. And we do so without expending an ounce of ATP. Now you might say, well, wait a second, we used ATP over there. Yeah, we did, but that ATP created the gradient that we can take advantage of. This is not the only place where that gradient comes into play. Every amino acid uses this. Most sugars use this. But that gradient is used for many other things beyond just moving ions and moving molecules back and forth across the membrane. It's an important gradient because it has potential energy in it. Does this make sense? Yeah? I don't want it to confuse you all. It should be pretty straightforward.
So, glucose needs sodium for it to be able to bind.
Right.
Sodium needs glucose for the parent protein to stay in the.
That's correct. That's absolutely correct. And I love this. I now have got the spinny wheel of death. Yeah. Yes, go ahead. It just, all right, so once it goes in, it can be used for whatever it needs to be used for. So if you're trying to maintain or keep the glucose concentrations low, you can convert it, or you can go ahead and you can add it to a chain of glycogen so that you're actually putting it into storage. You can break it apart through the metabolic pathways so that you're actually converting it into energy in the form of ATP. All these other fun things that you learned about in Biology 101. And we're still stuck in the spinning wheel of death. This is not good. I hate when this happens. Let's see what I can do here. No, don't worry. It's just this laptop is evil in all sorts of different ways. Let's see if I can. We'll just start the task manager. Trust me, it's still there. I can see everything right here. It's just evil. For 3 years or 4 years, I used the same exact computer, never had a problem with it. I got this new one, and I've had nothing but issues. I agree. Hold on one sec. I need this. Here's the fun thing. You get to see everything I'm doing here, and it's going to all be sideways. When you look at, if you watch the video later. Okay.